Okay, yeah, so this is a fairly different talk from the one that preceded it. Before, we're looking at structures that can influence properties. In this talk, I'll be talking more about how we actually get informative properties from quantum Monte Carlo itself. In particular, one that's very interesting, I think, and useful in many contexts is to be able to get the Fermi surface. So what I'll outline is a formal connection between the many-body ground state and the Fermi surface. And I'll demonstrate this in the context of the palladium cobalt oxide delaphosite system. And that allows for a comparison between quantum Monte Carlo data for the many-body wave function method and also with ARPAs derived from the same system. And finally, I'll talk a little bit about future application domains. Okay, so the Fermi surface and the ground state wave function. So knowledge of the Fermi surface is important for classification of many topological materials, for example. It's relevant for distinguishing between like Dirac metals, Dirac semimetals, Weil semimetals, etc. For certain topological states, you get this kind of tilting effect. But it's important to recall that the Fermi surface is actually a ground state property. We often think about it in terms of ARPAs, right, where we're ejecting electrons from the system. This lets you map the Fermi surface. But intrinsically, it's a ground state property. And I'll motivate that by looking at the band structure here, right? If you have the band structure, this line represents the Fermi energy. So while you can get it by depopulating levels around here, the totality of information contained underneath in this occupied C also uniquely defines the Fermi surface because it also contains information about where these crossing points are, where these bands cross the Fermi level that defines the Fermi surface. So there should be a way to get at this information within quantum Monte Carlo without having to do anything special at all. It should just be present in the ground state. Okay, and so how do you get it? Well, something that I'd say Ilkka Kalempa actually realized, he's sitting here in the audience, is that some of the secret for this might be contained already in some procedures applied by people doing positron annihilation experiments. So they also map the Fermi surface. In this case, they do it by putting positrons in the system, they annihilate with the electrons, and you get the similar momentum information out that you do from ARPAs. But they really are probing the ground state. And the information that they're measuring in that system is actually a measure of the momentum distribution of the electrons. So what's the momentum distribution? It's the kind of the K-space analog of the electron density. So if you have the density matrix, if you take a bracket with R on that, those diagonal elements in R is the electron density. The diagonal elements of K, momentum states, is the momentum distribution. So it's how many electrons have a momentum K, right? And that varies from no momentum all the way out to infinite momentum, right? And that's what the momentum distribution is. But what they showed, at least for a simple single particle system, a single slater determinant type system, is that if you apply backfolding, which is just to take all contributions from the extended zone scheme, momentum distribution, you backfold all those contributions, fold them all back into the first Brillouin zone. And so you end up with this kind of a periodic momentum distribution in momentum space in each Brillouin zone primitive cell. You can get information about the Fermi surface from this. And that backfolding procedure is called the Lock-Crisp-West procedure. And if you look at this procedure in more detail, you can see a bit more what it's doing. So, for example, if you take just a single block orbital's contribution to the momentum distribution, that's just that block orbital squared, right? This looks a lot like the contribution of one orbital to the density, has the same form for the momentum distribution. But if you end up going and taking this G-vector sum on this orbital and a little bit of math, what comes out is you actually just get a delta function. So all this structural information that came out from this orbital distributed through K-space, which also shows up in the extended momentum distribution, all of that collapses to a point with weight 1. And so there's an awful lot of information in the extended zone momentum distribution that's irrelevant to the backfolded momentum distribution. And this property is actually what allows you to get the information that you want. And what that the Fermi surface shows up as in this context is as step discontinuities in the backfolded momentum distribution that allows you to uniquely identify where the Fermi surface is. Okay, so what's that look like in a correlated setting? Okay, so here this is the definition of the one-body reduced density matrix. You're just doing this, you integrate out all electron coordinates but one, and you allow that remaining coordinate to be different. So that means it's a non-local object. Now, if you consider the momentum distribution in a crystal, then what you know about it is that since these larger density matrix as well as the Hamiltonian commute with translations, the eigenstates of the one-body reduced density matrix must also be block states, right? And so if you want to construct the momentum, the one-body reduced density matrix, it's going to be this bow tie of block states and occupation numbers. In a single particle mean field theory, like density functional theory, these are simply integers. These are ones and zeros. In quantum Monte Carlo with dynamic correlation or with wave function with static correlation, these become non-integer, right? So these actually take on values strictly between 1 and 0, but they can be anything in between there. All right, so let's say we did diffusion Monte Carlo. We get the one-body reduced density matrix. We take its diagonal element to get the momentum distribution, and then we apply backfolding, which is just a sum over G vectors. Okay, so we do this periodizing sum, this Lock-Crisp-West backfolding procedure. You similarly get this each block orbital out here summed over G that produces a delta function, and now what you're left with is the sum over K points in the Brillouin zone, a sum over occupation numbers that belong to that K point in the Brillouin zone, and it's attached to that place in the Brillouin zone. Okay, so but if you stare at this for a second, you realize this is a little bit weird. We've taken an object which is diagonal in K space. This is just the diagonal element of the density matrix, right? Think of like the density, for example. If you took the density and you did some operation to it, and we're getting out a sum of its eigenvalues. Okay, so that was a little bit surprising at first, that just by doing this backfolding procedure, you actually expose information about the eigenvalues of the density matrix, and not just and not have that information preserved or spread out because you're just taking the diagonal bits, right? So what's that from? That's a little bit interesting, but in the same sense, in this context, you can still get information about the Fermi surface by looking for step discontinuities in K space. The difference is you're going to have curvature toward the step discontinuities. That's going to be related to the renormalization of quasi-particle weight. That's different for a dynamical correlated system than for a mean field one. Okay, but there are some technicalities to this, which I'll go over just for a second here. So one is you actually can only afford to measure wave vectors out to a certain distance, right? You're limited to a finite choice in any calculation up to some K max. Well, what to do about the states outside of that? Well, in the positron annihilation experiments, they came up with various schemes to try and extrapolate out long tails of the momentum distribution before resumming, but those are all very approximate. And so if you do this sum just by truncating these to 0, you're missing a lot of weight. So this is, you can see there's a step, so there is a Fermi surface. These should have summed to about 48. We're missing about 2 electrons worth by having a finite K max that we have. So one thing that you can do instead, which is actually pretty good, but they can't do in the experiment, is you can instead just kind of hybridize and paste 2 things together. In this case, we use the DFT orbitals, the DFT momentum distribution beyond K max. And if you look at it analytically, it actually lines up very closely. It's just way, way out in this evanescent region. Gives you something much better than a simple model will. And when you redo the sum, you again get kind of conservation of particle number, which you'd expect. You have 48 electrons in one pocket and 46 in the other, where they become unoccupied, but you can also see curvature near the Fermi surface. So fine, you can do that with the momentum distribution. Something that stood out while looking at this is that since you're getting the sum of eigenvalues information, this can actually be recast as a partial trace of the density matrix. You're actually just doing a sum of the diagonal elements of the density matrix at a particular block K point. And so instead, if you wanted to actually, so that actually implies that the momentum distribution is unnecessary. Instead, you can just look at the density matrix itself and perform the trace directly. You'll recover the momentum distribution trace if you take the trace in plane waves. But you can also perform that trace in any valid block basis. And in this case, block states coming from DFT are going to be a rapidly convergent basis. And so you can, instead of summing up to a K max and having a lot of missing information, you can instead sum up to some kind of an M, some number of bands, right? Like in a CAS, a window in the excited states where you're going to have much rapidly decaying information and only need a handful of DFT states to get the information that you need. Okay, so enough talk about the methodology. What's this really look like? So we chose to apply this to delophocytes. And what do those look like? They're an interesting kind of layered system where you have, in this case, this is palladium cobalt oxide. Cobalt is sitting at the centers of these oxygen octahedra. So this is, if you looked at just this layer, it would look like just a layered 2D oxide, right? Of which some exist that are kind of like this. But in between those oxide layers, you have palladium atoms essentially intercalated. And they occupy this very strange bonding environment where they have these linear bonds. And what's interesting about this system in particular is that it has the highest in-plane conductivity known among oxides. Not only is it a full metal, but you have a ridiculously small kind of effective mass. You have a mean free path that extends at least microns in the material. It's very long. So, and you also have highly anisotropic conductivity. You have 1,000 times higher in-plane conductivity than out. And in DFT, at least, that means that your Fermi surface should have very close to quasi 2D structure. And indeed, in DFT, if you look at it, you essentially just have this cylindrical feature for the Fermi surface. And for a test case for us, this made it ideal because you don't need to gather as much information throughout the entire Brillouin zone. You can just do a cut. And so that's where we started with it. So next I'll show results from our many-body wave function, and I'll compare with ARPAs. So again, this is the sorted by index. This is what you get for that backfolded momentum distribution. So this is just sorted. But if you reorganize those different occupations in the Brillouin zone and select a contour value at the middle, so you know you're on the surface, you get this shape. It's a near hexagon. DFT actually gives us with some kind of wobbly curvature to it. And if you compare it to ARPAs, you actually get something that's very close. So here's ARPAs on a palladium cobalt oxide surface, here in this orange area, and here is ours in this teal color. So they're close. It's not exact, but also in the experiment, you have a couple of other things going on, right? ARPAs can be surface sensitive. You have surface charging effects. You can have some oxygen stoichiometry differences. And so some of this can be due just to slight differences in charge can change the volume of the Fermi surface. And that's what we think is actually going on here, because the volume of the Fermi surface is constrained by the electron count. And so if you see it shrink, it's going to be due to some degree of charging. But the shape is actually quite close. Okay, so in summary on this, I would say we've shown how to obtain the Fermi surface from nothing but a ground state wave function, and shown a connection between the Lock-Crisp-West backfolding procedure and partial traces of this momentum space partitioned one-body density matrix. We've shown that it's effective in this palladium cobalt oxide case with I'd say decent or good agreement with ARPAs. And in the future, it'd be good to extend this, right, to look at more interesting cases, you know, true strongly correlated systems, topological metals, things like this, that we really would like to have a link between benchmark quality theory and experiments like ARPAs or these positron annihilation experiments. So tools to compute this and post-processing of QMCPACK outputs exist. They're not yet released in the main repo, but if this is a topic that interests you, I'd encourage you just to come talk with me. We can kind of work things out, and I'd be happy to collaborate on this topic. All right, thanks. Yeah, where's the mic?
Oh, okay. Thanks so much, Jaron, for the really fascinating talk. I'm just wondering what makes the QMC Fermi surface different from the DFT?
So that's a good question. They actually should be closely related, at least in the trial wave function you put in, right? But we often use diffusion Monte Carlo to optimize which state we select, right? And optimizing the U value or the exact exchange fraction. And so it will get kind of dragged along for the ride in some extent. The curvature near the Fermi surface, of course, is entirely a product of diffusion Monte Carlo alone. And if you go in methods that are beyond DFT, so Josh just showed us some exciting developments for the carbon dimer. If we're able to scale those up to larger systems, then free ourselves completely from DFT, then we'll be an entirely self-consistent, self-sufficient QMC method. But this tool remains the same, and we'll be able to make these inquiries from whatever wave function we have access to.
Yeah, great, thanks.
Next question. Run out to get some logistics sorted. Any more questions? There's usually one over here, but
I think Shib's got one.
sure.
I'm like a way outside of this field, but like now that you've done the work to show that you can do it as a trace over like the K-space density matrix, is this like automated? Like, can you just take a material and then get it, just have Nexus spit out the Fermi surface?
Yeah, you should be able to automate it to a high degree. What I will say is that for efficiency reasons, there's probably some additional development that you would want to do to make it a little bit better. And that is that the density matrix calculation inside of QMCPACK doesn't really is symmetry unaware, right? So like in the molecular setting or in a defect or whatever, it just says all orbitals versus all orbitals for the density matrix. You'd save a lot of computation and hassle in memory if you could just say, just look at the diagonal blocks in K-space. So if we did that, that would speed it up to the point where we would want to do, very, very large calculations densely over the whole Brillion zone. You can still do it today, of course. It just costs a little more.